Alright, so for this section 1.2, we're going to discuss the linear equations in one variable, and this is just solving linear equations. The phrase linear from an expression standpoint is of the form something times x plus a number plus something else once every like term has been combined. So there are some names here I guess we can discuss. So the things separated by this plus would be terms. So these are terms. And the numbers in front are coefficients. So A here is a coefficient. I guess B is technically a coefficient, but coefficient really just means number in front. Boom, that's all I'm going to say there. Now as far as an equation goes, if you have a linear equation, it'll be an equation that involves linear expressions. So for instance, the equation 2x plus 3 is equal to 5, this is a linear equation, and here's how you solve. We'll subtract 3 to both sides first, or from both sides, however you want to say it, and then divide both sides 2. And doing this will leave us with x is equal to 1. That's our supposed solution. But we can actually check that it works by doing the following: plug it back into the original equation. So if you plug it back into the original equation, you get 2 times 1 plus 3 is equal to 5. If you simplify things on the left, you'll get 5 is equal to 5. And we get the same number on each side, so the equation has been satisfied. Okay, sometimes the linear equation won't be as nice. There's kind of like a worst case scenario where you have, I'm just going to make up numbers here, so be warned. Because when you make up numbers in math, the answer will never come out super pretty. In this case, it's not actually too bad. But let's see. So I'm going to move all x's to one side and all non-x's to the other side. That's the general, I guess, strategy here to solve for x. So we're used to having our solution to look like x equals, so I want x's to be on the left. If you have x's on the right, you'll just have something equals x instead of x equals something, but that's fine. So if we subtract 5x to both sides, what we'll end up getting here, if you add straight down, will be negative 2x. But notice, since we want to get rid of all non-x's on that side and bring them over to the other side, might as well take advantage of this negative space we have and add 7 to both sides to balance the equation. And that'll move all non-x values to the right. Add straight down, you get 20. Now we can divide by negative 2. And finally get x is equal to 20 divided by negative 2 is negative 10. And can we check this? You can check this. I'm not going to check it. You can check it. And I'll do one more example that's kind of similar to this, but it'll involve a little bit of simplification first. And that's the following. Okay, so let's see what happens here. The first thing we're going to do is we're going to get rid of parentheses by distributing. So distribute this 5. 5 gets multiplied to each of these. 5x minus 15. That 2 is still there. On this side, there are some things that can actually combine. X and negative 3x, for instance, combine. How do they combine? The number in front of x is 1. So 1x minus 3x will be negative 2x plus 7. Similarly, here on the left, these combine to negative 13. Since they have opposite signs, you subtract them and it gains a sign of the larger number. And now what you should notice is that what we end up with here is actually a similar situation to what I call the worst case scenario, of course after simplifying. And what we're going to do is we're going to do the same thing we did there. Move all x's to one side, just like this, and all non-x's to the other side. And on the left, we get 7x. On the right, we get 20. Dividing by 7 will give us x is equal to 20 over 7, which I'm going to leave like that. And again, the answer is kind of ugly, but hey, it's a number 2, so that's fine. And we'll see some more examples right now. All right, so here I wanted to continue to do more examples for 1.2, and there are a few cases that involve denominators, basically fractions. This is kind of a simpler case, and then the next example will be a little more complicated, but let's see. So in this case, where you have a fraction equals a number, or even worse, a fraction is equal to a fraction, remember that 5, we can always write as 5 over 1. What you can actually do here, fraction equals a fraction, you can cross multiply. So if we cross multiply as such, multiply denominators with opposite numerators, notice 1 times x minus 2 is still x minus 2, and then 5 times 3 will be 15. This is a new equation now, but it'll have the same solution, and even better, there are no denominators, there's no fraction in sight. Add 2 to the other side, x is equal to 17, and you can check this if you want, but again, this is it. Moving on to this one, something a little different happens. We could combine these on the left into one fraction, then we'll have this scenario, we can cross multiply. You can try that on your own if you want, and let me just say, if you want to do that, you would have to multiply top and bottom of this by 3, top and bottom of the next one by 4, so that you have the same denominator. You can combine those into one fraction and then move on in that fashion. But in this case, what I'm going to do is something a little more sophisticated. What I'm going to notice is that these denominators, 4, 3, and 6, have a least common multiple of 12. In other words, if you take a look at the numbers 3, 4, and 6, and you take a look at their multiples, let me just create a list like this, like a table if you will. Multiples of 3 are 6, 9, 12, what else? I guess 15, 18, 24, well, I guess 21, then 24, and so on. I don't need to go that far on the list, but it's just something that we can do. Similarly, for multiples of 4, there are 8, 12, 16, 20, 24, 28, and 32 if we go down to the 8th multiple. And for 6, you'll see the point in a second why I'm doing this. For 6, the multiples are 12, 18, 24, 30, 36, 42, and finally 48. Now why am I doing this? Well, these are all multiples of these numbers, but what are the common multiples of each of these three numbers? The smallest such is 12. See that? This is called the least common multiple. When it comes to denominators, we know this as the least common denominator, or LCD for short. So the LCD is 12. Notice it's not the only common denominator, it's just the smallest such common denominator, or common multiple in this case. So like here, 24 is another common multiple of the numbers 3, 4, and 6. And it's no coincidence that it's a multiple of 12. As it turns out, any common multiple of any numbers, any set of numbers, whether it be 2 numbers or 3 numbers or however amount of numbers, is always going to be a multiple of the smallest such common multiple. That's a little deep of a fact, but it's true. Now what I'm going to do is I'm going to multiply each of these by 12. And that's something, of course, we can do with an equation. We can multiply both sides of the equation by that number, or whatever number we want. In this case, the number we choose to multiply each side of the equation by is 12. And the reason being is that since 12 is a common multiple of each of these numbers, when multiplying 12 to each of these fractions individually, since each of the denominators will go into 12, we'll have cancellation. We won't have any fractions after canceling. So let's see that happen here. So this 12 will need to distribute. This 12 here is just cancel. 6 goes into 12 twice. So after applying the LCD multiplied to every term, we get 2x on the right. And let's see. Let me write it here, I guess. 12. When you multiply to this, 4 goes into 12 3 times, so I need to multiply 3 to the whole numerator. So I'll show that by actually writing it out. So I'll have 3 times the quantity 2x minus 3 for the first term, plus, if you multiply 12 to this, notice 12 and 3 cancel. 3 goes into 12 4 times, like that. So we end up with 4 times 5 for the next term. So I'm just leaving it like that just so we can see what happens as far as how this behaves when you multiply by the LCD. And in any event, let's simplify a little bit. So we get 6x minus 9 plus 20 is equal to 2x. Perfect. Now we again have, similar to over here, we now have an equation with no fractions, and we can solve this based on the previous examples that I showed you earlier. Combine like terms. move all x's to one side and non-x's to the other. It's at negative 4x. Good. And then divide by the coefficient finally. And we get our solution, and you can check as an option, but it's not required by any means. There we go. And there are a few more examples I want to do as well, so we'll see those right now. Okay, now for these next two examples, they're kind of similar to the previous examples we saw. The only real difference is that now we have x's in the denominators. So as it turns out, technically, these equations are not linear at face value. Meaning, after a little bit of algebraic manipulation, similar to what we did before, they may turn into linear equations, and then we can solve from there. So that's kind of what we're hoping for. Let's see what happens. So let's just try to do what we did before. Let's cross multiply. Remember, opposite denominators to opposite numerators. So on the left, I'll get 3 times the quantity 5x minus 4, just like this. And on the right, we get 2 times the quantity 5x plus 4, just like that. Great. Now, let's distribute to get rid of parentheses. So we end up with 15x minus 12 is equal to 10x plus 8. Great. Now this is a linear equation. We can move all x's to one side, all non-x's to the other. We get subtract 10x. And then using the negative space, we can add 12 to the right. Let's see, 15 minus 10 is going to be 5x on the left. And then on the right, we will get 20. Divide by 5, x is equal to 4. Now, the caution I give you is the following. When you have x's in the denominator, you have to check. The reason why is because it is possible that the x value you get will correspond to a 0 denominator when plugging back in. That's called an extraneous solution. There are multiple examples of extraneous solutions, but this is the one we'll be seeing in this chapter anyways, that involves having a 0 in the denominator after checking. In this case, it doesn't happen though, and you can just check by plugging it into the denominator. Notice the only denominator is 5x plus 4, and when you plug in 4 for x, you get 5 times 4, which is 20, plus 4 is 24. And just to show, I'm going to check completely. So when you plug x equals 4 into the original equation, here's what we get for the left side. We get 20 minus 4, which is 16, over 20 plus 4, which is 24. And that's supposedly equal to 2/3 according to the equation. And it actually is, because you can divide top and bottom by what? By 8. And when you divide the top by 8, you get 2. When you divide the bottom by 8, you get 3. So this question mark in actuality is a check, meaning x equals 4 is indeed a solution. So now we can move on to the next example. And again, just like we saw before, you can combine these into one and cross multiply. I'm not going to do that. I'm going to try to take advantage of the LCD technique we saw before. It's a little more difficult because we have expressions instead of numbers, but let me just show you. The LCD is just going to be the product of all of the distinct factors. Basically, product of all the denominators. X minus 4 times x minus 2. And notice here, x minus 4 and x minus 2 is there. So think about it. If you were to multiply this expression to each term, so imagine multiplying this by this, you have cancellation, so you're only left with 2. If you multiply this expression, x minus 4 times x minus 2 to this, the x minus 4's cancel, so there's no denominator. Similarly, if you multiply it to this, the x minus 2's cancel, so there's no denominator. So this LCD will work for us. And instead of me writing this multiplied to each of them and witnessing the cancellation, I'm going to share with you a little shortcut. It's a little visual, but just kind of try to keep up. I think we'll be okay. So we're going to take each of these 3 terms that I'm emphasizing on here in red, and we're going to pass them through this LCD and treat this as somewhat of a filter. And the reason why I call it a filter is because it's going to filter out the denominators via cancellation. So notice, if we multiply this to this first term, they both cancel and we're only left with the top 2. So we have filtered out the denominator for the first term. So let's see if we can keep up and follow for the second term now. If you multiply, and I can write it over here just so we can see it better. If you multiply the first term by the LCD that we're treating as our filter, x minus 4 times x minus 2, what cancels? That's right, the x minus 4, assuming you responded to that. The x minus 4s cancel, and all we're left with is 1 times x minus 2, which is x minus 2. Similarly, so that's for the second term. Similarly, for the third term, assuming it goes right here, the x minus 2s cancel, so the top 2 is only multiplied to whatever didn't cancel, which in this case is x minus 4. Perfect. So this is what we're left with, and this is indeed a linear equation. Let's solve it. Distribute the 2. So we get 2 is equal to x minus 2 plus 2x minus 8, just like this. Combine like terms. Perfect. Oh, I'm sorry. Jumped ahead a little bit. But yeah, negative 2 minus 8, they're both negative, so they combine and the result is negative, so it's negative 10. Okay, now adding 10 to the other side, we get 12 is equal to 3x. And now what do? Divide by 3. And our solution is x equals 4. Let me repeat. Our supposed solution is x equals 4. Remember, when your original equation had x's in the denominators, you have to check. There's no way around it. The good news is you can only really check into the denominators. So let's see. When you plug in x equals 4 into the denominators, well, here, what do you get for the first thing? You get 0. So right away, this is bad. As it turns out, this is what is called an extraneous solution. Meaning we got it as a supposed solution from applying the algebra correctly, but it's not actually a solution. It doesn't satisfy the equation. In fact, if you were to check this and plug it back in, I ran out of space here, but let me write it in the middle here. So if we were to check this, here's what we get. You would get 2 over 0 times, I guess 2, which is still 0, is equal to 1 over 0 plus 2 over 4 minus 2 is 2. So something like that, which of course kind of makes my stomach feel bad because you have 0 in the denominator. You never want to see that. The fact that we have 0 in any denominator, as soon as you see 0 in the denominator, run. Just kidding, don't run. Just say your solution would be extraneous, so it's not really a solution because x is not equal to 4, in which case there's actually no solution. Which could possibly happen. You could possibly have linear equations with no solution. And yeah, that I think ends 1.2.